time we're going to have kind of a different format. We're going to discuss some papers that have recently been published on the famed young sun paradox. So I hope that some of you will check out the link for that and maybe read them and show up and we can chat about those kind of formally. And then I think 2 weeks after that, we'll probably have a talk by John and maybe a Alphonse as well a couple weeks after that. And so if you haven't given a talk yet, of course, we always encourage you to do so. But I guess in the fall is when we can start looking for people to give talks on their research. So obviously Jim doesn't need an introduction, and I'll just let him go ahead and get started.
Okay. Yeah, I'm going to talk about Earth's energy imbalance, which is a very important number. We expected that Earth should be out of balance with space because we know that the amount of greenhouse gases in the atmosphere is increasing. And the physics is extremely simple. If you add gases to the atmosphere that absorb in the infrared part of the spectrum, then they make the atmosphere more opaque at infrared wavelengths, and you can calculate that very accurately. And if the atmosphere is more opaque, that means the radiation to space is going to arise from optical depth 1, but on average, but that height at which the atmosphere is sufficiently opaque is going to rise as you add more greenhouse gases to the atmosphere. And we know the temperature profile in the atmosphere, and it falls off with height, so it's colder at the level radiating to space. Therefore, that reduces the amount of energy radiated to space. So you've got a temporary imbalance between the amount of energy absorbed by the planet and the amount radiated to space. Therefore, the planet should warm up, but it takes time to warm up because of mainly because of the thermal inertia of the ocean. So there should be some imbalance as a function of time. And that imbalance is a very important number because it tells us how much warming is still in the pipeline. If we just multiply that imbalance by climate sensitivity, we get the amount of warming that's still in the pipeline if we know how sensitive the Earth's climate is to a forcing. And it also tells us how much we would need to change the atmospheric composition if we want to stabilize climate. Because if we reduce the amount of greenhouse gases, then that tends to reduce this imbalance. And so, for example, if the planet is out of balance by 1 watt per meter square on average, and if we wanted to restore the planet's energy balance so that the climate would stabilize, you would need to, and if, let's say, we reduce CO2, then you would have to go back to something like 335 parts per million to restore the balance. And that, of course, is more than the pre-industrial CO2, which is 280 parts per million, because the planet has already warmed up partly. And if we just want to restore balance with today's climate, we would just have to go back to 335 parts per million. But the complication is that, so we know this greenhouse gas forcing as a function of time very accurately. And the problem is that there are other forcings. Natural forcings like the sun and volcanoes occasionally going off, which reflect sunlight, so that's a negative forcing. And then there are human-made aerosols, which both reflect sunlight and affect cloud properties, presumably increasing the lifetime and the brightness of clouds by increasing the condensation that we get. Now, Andy Laces would say that this error bar is overstated. stated, is we could actually calculate the greenhouse forcing very accurately if we wanted to. But you would have to calculate it every place on the Earth, so you have to know the temperature profile every place on Earth. So you could, if you really wanted to, you could make that error bar smaller. But the problem is that this error bar, Andy would say, is understated. The truth is, based on just the physics, we can't even specify this aerosol forcing to this accuracy. The uncertainty based on first principles is extremely large. So how do we specify? This is a diagram taken from the last IPCC report, which shows the greenhouse gas forcing probability distribution function for estimates of the greenhouse gas forcing. So that's about 3 watts per meter squared. And then it gives, this is a distribution function for estimates of the aerosol forcing. And it has a kind of funny shape, especially given the fact that we're so completely ignorant of its actual value. But I think the reality is that it has, I think this is more a distribution function for what models would need in order to give something that resembles the actual climate change. And it so happens that most of the models used values of about -1 watt for the aerosol forcing. So we were involved in the IPCC runs also, and we had to decide what aerosol forcing we were using. And we really, I objected for a long time to the fact that we haven't measured this aerosol forcing, because the truth is we could measure it, but we haven't done that yet. So anyway, I asked my grandchildren, what is the forcing? And Sophie, my oldest grandchild, suggested that the net forcing was about 2 watts per meter squared. And she was trying to explain this to her younger brother with these 2 1-watt Christmas tree bulbs. But Connor could only count 1 watt. And so I didn't know for sure which one I should, but I thought Sophie's older and probably wiser. So we tended to go more with Sophie's estimate, and we used a net forcing of about 1.6 or 1.7 watts. Now, if that doesn't seem like a very good scientific method, you should see what the other guys did. So what they did, this is another chart from the IPCC document. So here are the greenhouse gas forcings, and sort of the technique seemed to be to use as many forcings as you could, and then get down to this point, and you can include some estimate for direct aerosol forcing. And that has a big uncertainty bar. And most models, or perhaps all of them, included some direct aerosol forcing. The estimate for the cloud albedo, the effect of aerosols on cloud albedo, that has a very large uncertainty bar. But then there's another aerosol bar which IPCC decided not to put on this diagram because the rationale was it's even more uncertain. The error bar is even bigger on the effect of aerosols on cloud cover. So they do have a section later in the toward the end of the IPCC report which discusses the next aerosol indirect effect. But I think, when you run the models and you get through this point, then or maybe part of this, you start to get results which look like the real world, so there's not very much incentive to add more aerosol forcing. And in fact, so our model, where we had an aerosol indirect effect and a direct effect, and a net forcing of about 1.6, 1.7 watts. It happens to give very good agreement with the observed temperature over the last century. But now the question is, are we getting the right answer for the right reason? So let's talk about climate sensitivity for a moment. So this is a graph of the oxygen isotope composition of these deep ocean dwelling Foraminifera. So there are these microscopic creatures that live in the ocean, forams, which have hard shells. They're, as I say, microscopic, very small. But when those animals die, the shell sinks to the bottom of the ocean and the sediments pile up. And you can now take a core of these ocean sediments, which has the shells of animals going back over millions of years. And this time period is the Cenozoic Era, which begins after the Cretaceous, so right after the dinosaurs went extinct. The Cenozoic Era starts. And at the beginning of the Cenozoic Era, it was very warm. It was so warm that there were no large ice sheets on the planet. And at the times when there's no ice sheets, then this delta 018 gives you a direct measure of the temperature at which the shells of this animal form. So the water molecules in the ocean, some of them have regular oxygen and some have this heavy oxygen 018. And of course the lighter ones move faster, and when these shells form and take their oxygen from a water molecule, the proportion of 016 versus 018 depends upon the temperature at which this shell is forming. But it also depends upon the amount of 018 in the ocean, which once you start to have ice sheets on the planet, then the water molecules that form the ice sheet have an excess of oxygen 16 water, because that molecule is lighter, it can escape from the ocean. It can evaporate more easily than the heavy water molecules. So the ice sheets tend to have more oxygen 16. So you have to separate the oxygen 16 and the ice volume effect from the temperature effect. And as a simple approximation, we assume that because we know that the total change in the oxygen isotope between the time when there was no large ice sheet and the depth of the last ice age, that total change was twice as large as you would get from the temperature change. Therefore, we said, well, let's just assume that it's half, that for this entire period, it's half and half. Half of it is ice volume, half of it is temperature. And you wouldn't think that would work very well, but at the places where we can check it, it actually works pretty well. At this time when Antarctica goes over, there has been enough data that you can estimate that you might have thought that, well, the ocean temperature won't change much. This will be mainly a case of the ice forming on Antarctica. But actually it turns out the ocean did get colder and by enough to account for about half of that. And likewise, the change between the current interglacial period and the last ice age, there's independent data which shows that about half of it was temperature effect and half ice volume effect. So anyway, so we have a record for temperature for the deep ocean for this entire 65 million years. And so here I've expanded the last 5 million years so you can see the glacial to interglacial oscillations. And then the last half million years are expanded here so you can see them still better. And now the point that I want to make here, okay, this on this long time frame, we know that the principal climate forcing that caused this climate change is change in the atmospheric condensation, because carbon dioxide was at least 1,000 ppm at the warmest times, and at the coldest times it was as low as 170 parts per million, and that's a forcing of more than 10 watts per meter squared. The alternative forcings could be something, the amount of energy coming into the system, but we know that the sun, although it's slowly getting brighter, it has brightened by only 0.4%, which is about a 1 watt forcing. And changes on the surface, the continents were already close to their present position 65 million years ago. So the change of albedo of the surface would not be significant. So CO2 is the main cause of these long-term changes. But these oscillations are, of course, associated with the perturbations to the Earth's orbit, which affect the seasonal and geographical distribution of sunlight on the planet. And that is a very small forcing. If you calculate forcing with just the impact of those changes on the planet's radiation balance, it turns out to be a couple tenths of 1 watt. But it's able to drive slow feedback processes. We know that the amount of CO2 in the atmosphere changes as a function of time over the last several 100,000 years from ice core measurements. And we know that the size of the ice sheets is changing, which is measured by the changes in the sea level. And the forcings associated with those two processes are quite large, several watts per meter squared. Now, they're actually both slow feedbacks, because if you look at these carefully, the temperature changes before the CO2 and methane change and before the ice sheets change size. So these are slow feedbacks that are causing the climate change to be so large, but they can be instigated by Earth orbital forcings or any small forcings, because it's a very sensitive system at this stage of the Earth's climate. But what we can do to estimate climate sensitivity is we can compare different climate states, such as the current interglacial period and the last ice age. And we know that the planet is basically in energy balance with space, averaged over a few thousand years in both the glacial time and the interglacial time. Because if it weren't, if it were out of balance by 1 watt per meter squared, you can easily calculate that's enough energy to melt all the ice on the planet or to change the temperature of the ocean by an amount which is not observed. So clearly the planet, on averaged over thousands of years, is very close to energy balance. And so we can, the factors that maintain the colder climate during the last glacial period are a combination of the changes in the atmospheric greenhouse gases and changes on the surface of the planet. And they maintained a global temperature change of about 5 degrees, which implies a sensitivity to these boundary forcings of about 3/4 of a degree for each watt forcing. This is a sensitivity which is relevant to the fast feedback processes in the system. So this allows, we're keeping these boundary conditions, treating those as if they were forcing and looking at the temperature change in the atmosphere so that the water vapor and clouds and aerosols and any the fast processes are included as part of that climate sensitivity. It's actually, we can check how well that sensitivity works for the entire 800,000 years of the ice core measurements. And it turns out it works very well. This is a comparison in which we've compared the calculated temperature to calculated from the greenhouse gas forcing and the ice sheet forcing, multiplying that forcing by that sensitivity of 3/4 of a degree for each watt, but then assuming that the polar temperature is twice as large, polar temperature change is twice as large as the global average temperature change. And that's based on just calibrating it from this one comparison from the Holocene to the last ice age. We know the distribution of temperature change over the planet pretty well for those two periods, and the polar temperature changed twice as much as the global average temperature change. And likewise, calibrating the deep ocean temperature change in the same way, the deep ocean temperature changed 2/3 as much as the global mean temperature change. But then those factors work for the entire period, except in the case of a polar change. The observed Antarctic temperature change was actually larger. And I think that's an indication that the local measurement at one point is not a good measure for this full range of climate change, because at these warmest interglacial periods, you're getting to a point where there's almost no sea ice around Antarctica in the summer. And you can begin to get larger temperature changes on Antarctica. And just to investigate that, so I've taken at each 1,000-year interval, so at 800 different intervals along this record, we just take the temperature and the forcing, the greenhouse gas forcing, in this case, the greenhouse gas forcing, just plot a scatter plot of the temperature change and the forcing for the greenhouse gases and for the surface albedo, and then for the sum of both of them. And what we see is that we get more or less straight lines for the greenhouse for when we compare to the deep ocean temperature. When we use the Antarctic temperature, then you get this curvature. When we get to the warmest temperatures, you're getting a sharper increase. And that, you would think the climate sensitivity should be more or less flat. We're not at a point where we're getting close to a runaway greenhouse effect or to a snowball Earth. So it should be more or less linear. And what this shows is that the problem is with the Antarctic temperature, where it is increasing. And there's another So it's not a good measure of global temperature at these warmest temperatures. There's another thing that's fishy about both of these, and that's this behavior when the temperature gets very close to the present temperature, where you've got this funny behavior. And the reason for that is that these, this sea level record is one that's constructed with the help of an ice sheet model. And in my opinion, these ice sheet models are too lethargic. But we use this anyway because they give a nice complete record. But there is independent sea level data, especially for the last several 100,000 years. And that is in pretty good agreement with this. So I thought it's okay to use this. But if we compare, we make this same kind of scatter plot with a set of sea level data which is based on an analysis of Red Sea records, which is going to give you more scatter because they have a hard time setting their time scale. You have separate time scales for the Antarctic ice sheet, CO2 amount, and for the Red Sea analysis. So you get more scatter, but what you see is there's no indication of that funny business at this end of the record when you're looking at data which is a more direct measure of actual sea level change. So I think this is this funny business here is the result of ice sheet model, which assumes that Greenland and Antarctica are stable. Okay, now in order to look at this more carefully, it's useful to define a climate response function. I mean, you would like to know, you apply a forcing to the climate system, how long does it take the system to respond and come back to equilibrium? So you'd like to know this for the real world. But what we can do is estimate it from climate models. And this is what the GISS model. This is the model that we used for our submission to the last IPCC document. And the interesting thing is that after 100 years, the model has only reached 60% of the equilibrium response, which, you know, it seemed to me that I suspect that this response function is too slow compared to the real world. But that's what we would like to know. But if you know the response function, it's very useful because you can calculate the expected temperature change due to any forcing history very simply, because that's the response function is the Green's function for global temperature change. You just have to integrate the forcing that was added in 1880 should be multiplied by the response function for 127 years if you want to know the response in 2007. And then you just integrate that, and as I say, it takes 10 to the minus 7 seconds to calculate that, and you get essentially the same answer then as the GCM. It differs just because of the noise on the response function curve, and therefore but okay, so we can use this to do some interesting calculations. This is just the response function on the shorter time scale. So it's characteristic of it is you get a quick response in the first 10 years of 40% or more of the equilibrium response, and then the rest of the response comes very slowly. This is what Isaac Held calls the recalcitrant response. And presumably this is characteristic of the real world, but I think it's not realistically portrayed by the model. But that's the question. What is the real response function? So before I gave a talk at AGU a couple of years ago, I asked GFDL scientists and in-car scientists and Hadley scientists for their response functions, and I was surprised that most of them didn't have them. They're very fundamental, so they're very useful. But the one that did was in-car. They had run, I mean, most of groups, or probably all of them, run a double CO2 experiment, but they don't usually run that for several thousand years, which is what you have to do if you want to get the response function. So this one is very similar to ours. It turns out that I could tell, although they couldn't give me their response function, they could give me runs for 1% per year change in CO2. So then I can compare that with the GISS model, and you can see that our model actually responded faster than the GFDL model. And the same is true with the Hadley model. So although I thought, the reason I think that our model is too slow is because I know that the thermocline in our model deepens, and so it puts too much of the ocean into available for thermal inertia. And also the Antarctic, in the Southern Ocean, the mixing of chlorofluorocarbons is faster in our model than it is in the real world. So we probably have too much thermal inertia of the ocean being available. And so I was surprised that these other models are equally slow or slower. And I think it's because of common problems, both with the deep mixing and with the parameterization of subgrid scale processes, which they tend to all use similar parameterizations. And I think they're too diffusive. So I just arbitrarily define some alternative ocean response functions to compare with the one that the model calculates. We know that, and so I took two cases. So the model has 60% response after a century. So I took one with 75% and one with 90%. It can't be so slow as that. So fast as that, because once the ocean surface has responded, then that shuts off the flux of energy into the ocean. And if you look at paleoclimate data, then you would not expect the deep ocean temperature to respond on any. Its response would be very limited. It would take a very long time. And the deep ocean actually does respond, so I would not expect it to be as fast as the fast one. But we can investigate this because there are basically two unknowns. Two unknowns are the aerosol forcing and the ocean response function, climate response function. And we have one good piece of information, and that's the warming that has occurred over the last century. And the other fundamental information that we need in order to get a unique solution is the planet's energy imbalance. But anyway, using this Green's function, the planet response function, and three different response functions. The slow one, which is the one our model has, and the intermediate one, and the fast one. We can then find, well, what aerosol history will give the best agreement. And you can get agreement, of course, with any of these response functions by multiplying the aerosol amount by a factor which gives the best agreement. But then it implies, so the red curve is the best agreement in each case. But that then implies a planetary energy imbalance, which is about 1 watt per meter squared if the slow response function is right. And that's what our 3CM model kelvins. We should have an imbalance. The planet should be out of balance by about 1 watt. The intermediate response function has more like 0.6 watts, and the fast one is more like 1/3 of a watt imbalance. So then the question is, what is the real planetary energy imbalance? Well, that means you have to measure the heat content of the ocean, how rapidly that is changing. So we've been saying for many years, this is the most important measurement that you need to make. In the middle 1990s, I went to a NASA ocean meeting, and we were supposed to come to the meeting with our recommendation for the 3 most important measurements to be made. And not trying to be a smart ass, but I said the most important ones are ocean heat storage, and ocean heat storage, because it's so fundamental. We have to know how much the planet is out of energy balance. Finally, in the last several years, we began to get measurements that allow us to address this. And that requires measurements over the whole ocean. There have been measurements at places where ships go, but that's not good enough. You have to have measurements all over the ocean. So there are now about 3,000 of these Argo floats, which are distributed around the world ocean, and they have an instrument package that yo-yos down to 2 kilometer depth and yo-yos back up, and measures the temperature, among other things. And so we can finally begin to address this question. And so then it becomes worthwhile to also calculate the other terms in the planet's energy imbalance. The atmosphere has very little heat capacity, so its contribution is less than 100th of a watt. But the continents are getting warmer. We have these boreholes in the continents where we can measure the temperature as a function of depth, and we observe that the ground is getting warmer. And it contributes a couple hundredths of watt per meter square. And ice is melting, and it takes energy to melt this ice, and it's up now to more than 1 watt per meter square. And interestingly, the biggest term, or approximately the same as the land, is now the melting sea ice, which takes energy to melt the sea ice. So you can add those up, and it comes up still to less than 1/10 of 1 watt. And the ocean heat up, you can attempt to calculate the heat uptake in the pre-Argo era, but it's very uncertain, and the noise is, these are, I think, 6-year running means of the trend. And this is Levitas in green and Ryman et al. In blue. And it's pretty clear from review papers that the Levitas approach, which tends to have the results at a given ocean volume relax to climatology, it underestimates the heat uptake. But in any case, it's in the Argo era, we know it pretty well, and it's really only the last 6 years where they are willing to put an error bar, which they say is 0.1 watts, or actually average as its contribution to the planetary energy imbalance, it would be 0.07 watts. But that is not accounting for systematic errors that might still exist in the observing system, which even with the Argo floats, they found that they did have some systematic problems which they hope they have taken account of now. But anyway, that's a certain value, and we can now compare the sum of those non-ocean terms plus the Argo data with the calculations for these 3 different response functions. And
it turns out that the Argo data is in good agreement with the intermediate response function. But there's no way that you can make it consistent with this 1 watt that the slow response function would imply. I think, I mean, there was been discussions about this in the literature the last couple of years, where Kevin Trenberth had pointed out that there was some discrepancy between what he thought the energy imbalance should be and what the ocean data was telling. And this is kind of a smooth curve, which I don't know quite how he constructed this, but he thought there's some imbalance, some missing energy. I think that's not actually the case. It actually agrees very well with the calculation, provided you're using this intermediate response function. But why? So one question is, why did the imbalance decrease over the last several years? And we can investigate that. This is the CO2 growth as a function of time, the annual increase in CO2 compared with the IPCC scenarios. And this is the total greenhouse gas force growth rate, which not always recognized, but this was actually increasing most rapidly back in the late 1970s and 1980s, and it was going up about 5/100ths of a watt per year. And then it decreased significantly, mainly because the CFC's growth rate decreased, and methane's growth rate decreased. So the total forcing is actually not increasing faster than IPCC scenarios. But in any case, it declined, and that has leveled out pretty much the last couple of decades. And another forcing is solar irradiance, which has this variation of about 1/4 of a watt with the solar cycle. And the last 6 years, the Argo data is right at the minimum of what was the deepest solar minimum in the period of measurements. And then, okay, so then we can do these calculations with the response function. And we find, okay, if the same Green's function can give us both the temperature change due to each of the forcings. This is the greenhouse gases, the aerosols, and the sum of the greenhouse gases and aerosols, where the aerosols have been specified to be that which gives the agreement with the medium response function. And what you see is that the two principal forcings, greenhouse gases and aerosols, cause this imbalance. They cause the temperature change, which is the major part of the observed temperature change. But they also cause this energy imbalance, which flattened out because of that decrease in the greenhouse gas growth rate. But because it flattened out like that, that allows small forcings to have a noticeable effect. And one of the interesting effects is the volcanoes. The Pinatubo aerosols gave us this big negative forcing and a cooling effect in 1991, and that only lasted for a couple of years. So you wouldn't think it would be affecting things in the last 10 years, but actually it does. It's because of after the aerosols disappear, they're no longer
influencing the amount of sunlight absorbed by the planet, but they're still influencing the heat radiation to space because they caused the cooling of the ocean. And therefore, you continue to get this rebound effect after the volcanic aerosols are gone. And that then causes a decline in the radiation imbalance in the last decade. And the other thing is the solar irradiance, which here I've expanded the scale, but you can see that it does, because we're at a solar minimum, that caused some decline in the radiation imbalance. So, so I think that the planetary energy imbalance is about 5 or 6 tenths of a watt. And if it's half a watt, then in order to restore planetary balance and stabilize climate, you'd have to reduce CO2 to 360 parts per million, other things being equal. If it's 3/4 of a watt, and I think averaged over a solar cycle, it might be more like 3/4 of a watt. If that's the correct number, then you have to reduce to 345 parts per million. So anyway, it's an important number, but in order to understand this, we would like to have a model that really simulated this correctly, and I think that requires a model, an ocean model that mixes ocean water and heat more realistically. But that's what we're hoping that this collaboration with John Marshall and with Vittorio Canuto's small-scale mixing approximations or approaches, maybe we can get a more realistic ocean. If in fact I'm right, that is, our ocean is mixing too much. But anyway, that's the story.
Jim, your comment was that for the paleoclimate scenario, particularly the ice ages, the short-term climate sensitivity was about 3/4 of a degree for what is good. Do you want to comment on what the climate sensitivity is for the long term, including the slow change?
Yeah. I actually have a section on this in this paper, which we finished this week. I've been saying that for the last several weeks, but I think it's useful to define a sequence of climate sensitivities depending upon what feedback should include. I think the next logic, first of all, that the fast feedback climate sensitivity, I assert, is very accurately known by this data for the last 800,000 years, and that it's 3/4 plus or minus 1/8 degree. So very accurately. Now, if you look in the literature, they got a huge range, and the reason is they make this. The biggest reason is that they make the same mistake that we made in our 1984 paper on climate sensitivity in the Ewing volume, where in talking about sensitivity, we decided, in a climate model you can put in or take out any processes you like and see what is the impact of that. Well, likewise, if you're comparing these two equilibrium states, the ice age and the interglacial, you can say, well, what is the sensitivity if I consider this thing to be boundary forcing? And we decided to include the surface albedo and the greenhouse gas amounts and an estimate of tropospheric aerosols, where we put in a small number, half a watt or something. So it didn't really affect the results. But nobody knows the aerosol forcing between the ice age and the interglacial. You can put in any number you want. So if you're if you like low climate sensitivities, for example, when Peter Hillock and Ulrike Lohmann wrote a paper on climate sensitivity using the glacial and interglacial, I could have told you beforehand they're going to get a low sensitivity. They put in a aerosol forcing of 3.3 watts. Then they come out with climate sensitivity of 1.5 degrees for double CO2 instead of 3 degrees. Well, and they only put in dust aerosol forcing, but there are lots of aerosols. We don't know how they're changing. So it's a big, as soon as you say, I'm going to estimate the sensitivity for those 3 boundary conditions, then you're guaranteed you can't get an accurate answer. But if you say, I want the sensitivity to these 2 major boundary forcings, the surface albedo and the greenhouse gas amount, then you can get a very precise sensitivity to those 2 forces. And it is 3 degrees for double CO2 or 3/4 of a degree per watt. But now the next useful climate sensitivity is to say, well, what if we recognize the surface albedo? And this fast feedback sensitivity is pretty relevant to the decadal, to right now, until the ice sheets begin to either get smaller or get darker because they're starting to melt. If we say, I'm going to use the observed greenhouse gas as a forcing, then the logical sensitivity that you want, including slow feedbacks, would be all the fast feedbacks plus surface albedo. And that we can, in fact, look at the record and infer what that sensitivity would be. It turns out, well, it's actually implicit in this, the fact that the albedo, okay, this is greenhouse gases, and this is the surface albedo, and they're both providing about half of the forcing over that period. So if you include, if we treat the greenhouse gas changes as the forcing, then the sensitivity is 6 degrees for double CO2 for that range of climate states. The thing is that sensitivity depends upon climate state. So it is different if you go in this direction. For climates in this sort of range, the ice albedo of these things has become very large, and the ice sheets are essentially doubling the sensitivity. But if you go toward a warmer climate, they're not going to be as effective. However, what we pointed out in our target CO2 paper is that if you look at this total interval from here to here, which is where we are today, the amplitude of that is almost as large. So it's almost 6 degrees for that total range, but most of it is coming in at the time you lose Antarctica. The small shrinking of Greenland and Antarctica when you are just partway there to the Pliocene, for example, is not going to give you a doubling of your sensitivity. So that's, but anyway, I think that's a useful sensitivity that includes one slow feedback, because it's very logical to say, first of all, we know, in the last century, we know exactly how greenhouse gases have changed. So we can just specify them. And we can even project forward with carbon cycling models. And in those carbon cycling models, we can take account of the expected temperature change. So rather than trying to introduce everything into a sensitivity, I think it's one useful sensitivity is fast feedbacks plus surface albedo. However, Another sensitivity that's very useful is one in which instead of taking greenhouse gases as the forcing, you take CO2 as the forcing. Because when you try to figure out what greenhouse gases have been changing on the long time scale, it's very hard to get data on CO2, but finally they're beginning to get these proxy measures of CO2 are beginning to come into pretty good correspondence. There's a paper in Press which now makes it look much, and it turns out it's probably like 1,000 ppm at the peak of the Cenozoic. But if you did that, because in this change from today's climate to the last ice age, 25% of that greenhouse gas change was methane and N2O. So if we and there is evidence, people who've tried to calculate when we go to still warmer climates, are methane and N2O going to continue to increase the way they did from the ice age to the glacier? And the answer is yeah, probably they are, but we don't really know. But with the chemistry models, they've Beerling has estimated that yeah, you continue to get additional forcing from these non-CO2 gases. And if you continued at that same proportion, where you're getting 1/4 from the total greenhouse gases from the non-CO2 gases, then that would imply climate sensitivity of 8 degrees for double CO2 when you have the ice sheet feedback. But of course, once you get to this point, beyond that, then the greenhouse gas forcing is 3 degrees for double CO2. You don't have any more ice sheet. You don't have any more surface albedo feedback. And so even if the non-CO2 greenhouse gases amplified that by this 1/4, then it would be 4 degrees for double CO2. And that's pretty consistent with the data on climate change over this total interval. Now that's 2 levels on top of fast feedbacks. But there's still another one. And that is, well, what if we let CO2 be a feedback the way it really is? Well, then the sensitivity is going to get even higher. For climates that are in this part of the historical record, climate sensitivity becomes very high, which is what we know happens to be the case, because look at the huge amplitude of these climate changes. I mean, New York City was under more than 1 kilometer of ice, or a large amount of ice, which was much taller than the Empire State Building, driven by a forcing of a couple tenths of a watt. So the climate is very sensitive when you include the greenhouse gas slow feedback. There's some limits on those, and there are also negative feedbacks that come into play. And you can see them, for example, in the case of the pediment. Well, you got this huge, presumably you got this huge injection of methane, which turned into CO2, and gave you this warming of, which is actually understated in this graph, of several degrees, at least 5 degrees Celsius. But then, of course, then the system begins to take up that CO2. It would take it up faster if you got more CO2 in the atmosphere. And over 100,000 years or so, it gets back onto a curve which is dictated by the source, by the magnitude of the source. I guess that's telling us that we've used our time. That's interesting. Good time. So anyway, that sensitivity, if you start to try to include all the slow feedbacks, then you've got to really start to worry about, you're getting so close to exploding that you have to worry about the negative feedbacks that come into play.
Years ago, you gave a talk similar to this one where you stated that you felt that our current ice sheet models didn't allow for rapid melting processes, and that as a result, the potential for direct climate change was significantly underestimated. And I was wondering how that would play into the idea that the intermediate climate response function might be the one that fits best and would it continue to fit best if there were the direct climate change?
All we're putting in is the fast, in that, those calculations, I should have made clear with the Green's function approach, we're putting in the climate response function of the model with, of course, no slow feedbacks. So that, on the time scale, I think even this century, you'll start to get some slow feedback. You'll say that ice sheets are going to begin to respond, and at least, and it will affect their surface albedo. That's when you can see that the area that's melting on Greenland is increasing as the planet is warmer. I think we're not that far from starting to get melting on part of the Antarctic ice sheet, the longest part of the summer. So that, it's not, you're not going to see a big effect of that on a few decades. I don't know. That's the interesting question. We don't know how fast ice sheets can respond. That's why the gravity satellite data is so important. It does show us how the mass balance is changing, and the mass loss is accelerating. I mean, there is a limit as to how fast these things can go. Once the ice sheets start to melt too fast, when they start to cool off the ocean, that puts a brake on the rate of warming.
I'm puzzled by, you refer to these Milankovitch forcing as if it was a scalar. I thought the whole idea of a Milankovitch forcing is it's a seasonal variation of insulation, not just a number. It's a number with a curve on it. So I don't understand
that's why
treating it as a scalar.
Yeah. The Milankovitch forcings are perturbations of the Earth's orbit and the inclination of the spin axis, which affect the geographical and the seasonal distribution of the radiation, especially the tilt, which affects the geographical. When you tilt, the tilt is greater, then you get more sunlight at poles, and that tends to melt polar ice sheets. But the instantaneous forcing is, if you can calculate, it's just a couple tenths of a watt. I mean, so it's giving you more sunlight hitting the ice sheets. So, but that instantaneous forcing is not a good measure of the expected climate effect, and you begin to get some feedback. As you get some melting of ice, then that will make the planet warmer, and as the ocean gets warmer, it gives up CO2, and so the slow feedbacks then come into play, and they're instigated by that very weak forcing, and we don't have a way to translate the Earth orbital perturbations of the seasonal and geographical distribution to a forcing which is actually going to give you the observed climate change. It's a very complex thing. It's going to change as you begin to get some change in the ice sheets. Then, so that's the thing that people have been trying to figure out for a few decades.
I mean, a better way to think about that is to ignore the global change at all and just say, well, there's a great efficacy, a bigger efficacy of climate forcing that's projected into the northern hemisphere high latitudes, which that's what Milankovitch demonstrates. And the size of the forcing there is in the 10s, 20s, 30s, 40 watts per meter squared, averaged over the whole season. So those are pretty, I mean, they're not small changes, they're very large changes.
Yeah,
much larger than the regional changes associated with it.
I didn't understand your answer.
Okay, the forcing, the radiative forcing on a regional scale is tens of watts, 20 or 30 or 40 watts.
But then there's another forcing of the opposite side on another season or another part of the planet. So when you average those up, you get a very small number. But what's really important, and the fact is, it's use the word efficacy. This one forcing of 30 watts here might have a greater efficacy than the opposite forcing at a different part of the planet. And that's why you get an effect. But because these things, these geographic patterns and seasonal patterns are complicated, you're going to need nobody has figured out how to convert those into a prescription for what the